Calculating the enthalpy of dissolution. When ionic compounds dissolve in water, whatever dissolves will fully dissociate. And that is the example that we're going to observe today as we dissolve sodium hydroxide and ammonium nitrate in water inside a coffee cup calorimeter. We can use the solubility table to determine whether ammonium nitrate is soluble in water, and we find that all nitrate-containing compounds are soluble with no exceptions, so ammonium nitrate will be soluble. Similarly, sodium hydroxide is soluble in water because the first rule is if we have a group 1 metal cation like sodium, then all our compounds will be soluble with no exceptions. Calorimetry is a technique that we use to measure the heat energy that is exchanged during a chemical or physical process. The process of dissolution is a chemical process because if we go back to our chemical equations describing this process, we find that we start with ammonium nitrate in the solid state, and we end up with ammonium ions that are surrounded by water molecules and nitrate ions that are also solvated by water molecules. The calorimeter that we are going to use today is a coffee cup calorimeter, and it is a device that is designed to isolate the system undergoing the process and to accurately measure the heat flow. A typical coffee cup calorimeter will have 2 nestled styrofoam cups with a lid. The lid will have 1 or more holes on it. In this case, it'll have 2 holes. 1 hole will be designated for the thermometer that will allow us to monitor the temperature changes occurring through the process, and the other one is a stirrer to allow us to fully homogenize our solution and accurately measure the temperature change associated with the full dissociation. As a result, because we are assuming we have an isolated system, the heat that was generated by the dissolution or absorbed by the dissolution will be absorbed or released by the water. Here we're going to make an assumption. The calorimeter is an insulated system. If there is any heat exchange, it will only occur inside the calorimeter. So with that assumption made, we're going to explore 2 experiments. In the first one, we're going to take 2.08 grams of sodium hydroxide pellets, and we're going to add it to a coffee cup calorimeter. Inside the coffee cup calorimeter, there is 47.45 grams of water, initially at 21.3 degrees Celsius. And as the sodium hydroxide is dissolved and the solution becomes homogeneous, the temperature rises to 31.0 degrees Celsius. The task is to calculate the heat change associated with the dissolution of the sodium hydroxide pellets. And here we are going to make some assumptions. First, that the calorimeter is an insulated system. If we need to make more assumptions, feel free to add to this list. In step 1, we determine the heat that was absorbed by the water. And the phrasing is correct here. If the temperature goes up, heat had to be absorbed by the water. The heat of the water is the mass of the water, which is 47.45 grams, times the specific heat of the water, which is 4.184 joules per gram Celsius, times the temperature change of the water with the final temperature first, 31.0 degrees Celsius, from which we subtract the initial temperature, which is 21.3 degrees Celsius in this experiment. We perform the calculation and find that the heat of the water is 1,926 joules. And with that, we're ready to move on to step 2. Determine the heat released by the dissolution of the sodium hydroxide. If our assumption is correct that there were no heat exchanges outside of the dissolution of sodium hydroxide and the water that was in the calorimeter, we can say that the heat of the water has to be the same as the heat of the dissolution with opposite sign. So there we find that the heat of the dissolution is minus the heat of the water, which is minus 1,926 joules. We are ready for step 3, which requires us to calculate the moles of the sodium hydroxide dissolved. For that, we're going to take the 2.08 grams of sodium hydroxide, and we're going to convert it into moles. On top, we say 1 mole of sodium hydroxide, and on the bottom, we say 40 grams of sodium hydroxide. From here, the grams of sodium hydroxide can cancel, and our answer will be in moles of sodium hydroxide, 0.052 moles. Notice that the question changed. Instead of calculating the heat of the solution of sodium hydroxide, the question is now asking for the molar enthalpy of dissolution. For that to be calculated, we needed both the heat of the solution and the moles of sodium hydroxide, because then we're going to take the heat of dissolution, which is minus 1,926 joules, and we're going to divide it by the moles of sodium hydroxide that we just calculated, 0.052 moles of sodium hydroxide. When we divide these two values, we will determine the enthalpy change associated with the dissolution of 1 mole of sodium hydroxide, the value of which is going to be negative 37,038 joules per mole. Because it is a fairly large number, it makes a lot more sense for us to express the enthalpy change of the solution as kilojoule per mole, minus 37 kilojoules per mole. If we want to know how successful our experiment was, we can always look up the enthalpy of the solution for the sodium hydroxide in water and compare our determined value to the accepted true or literature value. Let's move on to our second experiment. Here we're going to take a 4.48 gram amount of ammonium nitrate, and we're going to add it to a coffee cup calorimeter. Inside that coffee cup calorimeter is 48.40 grams of water, initially at 21.3 degrees Celsius. And as the ammonium nitrate fully dissolves and the solution becomes homogeneous, the temperature falls to 15.8 degrees Celsius. The task is to calculate the heat change associated with the dissolution of ammonium nitrate. And step 1 would normally be calculate the heat absorbed by the water. Here, the heat is not absorbed by the water, but rather released. The heat of the water is equal to the mass of the water, 48.40 grams, times the specific heat of water, 4.184 joules over gram Celsius, times the temperature change, final, this is the 15.8 degrees Celsius minus initial, 21.3 degrees Celsius. After we complete our calculation, we find that the heat released by the water is 1,114 joules. And because it was released, it's going to have a negative value. And it makes sense because we're subtracting a larger initial temperature from a smaller final temperature. In our next step, we're going to determine the heat of the reaction, which is the opposite of the heat of the water. So it's minus 1,114 joules, or we can say that the heat of the reaction is 1,114 joules. We calculated the heat change associated with the dissolution of ammonium nitrate. And so if there are no additional questions, we can stop here. This is our answer. But if we change the question and say, what is the molar enthalpy of the solution, then we need to do 2 additional steps. Step 1 is to calculate the moles of ammonium nitrate. So for that, we're going to start with the grams of ammonium nitrate, 4.48 grams. And we are going to multiply it by a fraction, where on the top we have 1 mole of ammonium nitrate, and on the bottom we have 80 grams of ammonium nitrate. This fraction simply means 1 mole of ammonium nitrate weighs 80 grams of ammonium nitrate. By canceling the grams of ammonium nitrate, we're going to have our answer in moles of ammonium nitrate, 0.056 moles. Once we have the moles and we know the heat absorbed by this many moles, we can determine the molar enthalpy of the solution. We're going to take the heat of the solution and divide it by the number of moles. For us, that means 1,114 joules divided by 0.056 moles. And if we calculate the value, it is 19,893 joules per mole. We should convert this to kilojoules per mole to make it a more manageably sized number, 19.9 kilojoules per mole. And with that, for both experiments, we determined the enthalpy change associated with the dissolution of 1 mole of either sodium hydroxide or ammonium nitrate. And we also found that the dissolution of some ionic compounds will cause a rise in the temperature of the water, and others will cause a decrease in the temperature of the water.